Hi, welcome everyone. This is the week 1 of the NPTEL session of the course Introduction to Algorithms and Analysis. So, in this week, the topics covered were basically insertion sort, asymptotic analysis, and like basic analysis and workings of merge sort. Right, so the focus was primarily on the asymptotic analysis of these two algorithms, and insertion sort was took as the prime example to discuss most of the workings of how we do the time analysis or the space analysis, like asymptotic analysis of sorting algorithms or any algorithm in general. So what I'll be doing is I'll be just taking problems and discussing them here. Yeah. Now let me lock. Yeah. Okay. So let us just start with the problems. So the first problem is if f of n is of the order of g of n, right, and g of n is of the order of f of n, right, so the function is equal to the order of the other, then is f of n equal to g of n, right? So it is basically asking, is f of n, or like given that, just leave it, we can write it in mathematical notation as O of g of n combined with the other condition O of f of n. So these two, do they imply that they must be the same functions, right? So if they have the same order, they must be the same functions. So is this true or false? So we can take a very simple example, right? So since both are the complexities of the other algorithms, right, so we can take, let's say, example, right? Let's say f of n is an O of n algorithm, right? So let us say this is n plus c, right? Let's say this is, let's keep it general, right? So c1 n plus c2, right? Like we are taking the simplest case, and then g of n is c3n plus c4, right? So from this, what is the complexity of f of n, right? That is basically n, right, because this is linear in n. And similarly, the complexity of g is also O of n. Right? But if we see that this complexity, right, now this complexity can be written in any linear form that we know, right? So for example, complexity of n plus 1, right, can be written as n plus 2, right, and complexity of n plus 2 can be written n plus 1, because basically this n is the primary variable here, basically the order or the degree of n, right? So simply by this we can see that these two does not need to be the same, right? So C1 does not need to be equal to C3 and C2 does not need to be equal to C4 for these conditions to hold, right? So this is basically a false statement, right? So f of n, or if we have to just write it properly, then O of g of n, and if g of n is the complexity of f of n, this does not imply that they are the same functions, right? Because complexities, they only depend on the orders of the order of n, right? Not on the constants multiplied or added to n, right? Unless, like, given that the constants are very less than n, because it's an asymptotic analysis. So this is a basic question about complexities of any general functions and how the complexities can be the same even if the actual representation of the function is different. Let's take the second problem. So what operation does the insertion sort use to move numbers from the unsorted section to the sorted section of the list, right? And the options are finding the minimum value, swapping, finding a pivot value, and D, none of the above, right? So we have to see what the question is saying first, right? So it is asking what operation does the insertion sort use to move numbers from the unsorted section to the sorted section, right? So in insertion sort we do find the relative minimum number, and there is but this finding does not tell us how we change this number or how we arrange the numbers again to put the number from the unsorted section to the sorted section, right? We find the minimum number, but then what do we do with it? That is what the question is asking. So basically, whenever you find the minimum value, right, we swap it, right? So if we have a section like 1, 3, 2, 4, 5, right? So in this particular thing, in the first pass there is nothing to be done, but in the second pass, right, when we start from here from this position, right, when we start from this position, we can see that there is a minimum number here too, right? So we have found the minimum number, but what do we do then? We swap this number, right? So the array becomes like this, right? So this array becomes sorted after one swapping, but swapping is the mechanism that we used to actually move the number from the unsorted section to the sorted section, right? Because unsorted section is to the right and sorted section is to the left in insertion sort. So yeah, the answer should be swapping. Now problem 3. Let's say given the array, let's call that, let's not call it anything, but let's work on this array. Given the array, what will be the order of elements after third iteration, right? So it's not, this question is not asking us, oh yeah, one more thing, if insertion sort is used, right? So this problem, it is not asking us to sort this array completely. It is asking what will be the state of this array, or what will be the sequence of numbers after the third iteration of insertion sort is performed, right? So let us start with the given sequence 17, 31, 13 and 2. Okay, so what we do, let me space it out a bit. 17, 31, 13 and 2. So what do we do in insertion array? We start with the first element, right, and we take it as the key, and we search for the next smallest value, or not the smallest, or the value that is the first value that is smaller than our key, right? And whenever we find that value, we swap it with the key. Okay. Yeah, so we find the smallest value in the unsorted array, and then we swap it, right? The next smallest, basically. So we start with this and we start searching. So 17 is indeed smaller than 25, right? So after first iteration, so these will be swapped. So this will become 17, 25, 31, 13 and 2, right? Now this becomes the sorted section, and this becomes the unsorted section. Okay, so now again what we do, we take the key, right, that is 31, and then we put it at its respective place in the sorted section, right? So this will come right here after 25, right? So this becomes the unsorted section, and this becomes the unsorted section after second iteration, right? So basically in insertion sort, we just take the first value from the unsorted array and put it in its respective place in the sorted array, right? So no searching for the, basically we are not searching for the next minimum, we are just searching for the place of the first element of the unsorted array in its respective place in the sorted array, right? So what happens in the third iteration is we take 13 and we find its place in this section, so it will come before 17, so this will be 13, 17, 25, 31 and 2. So this is the unsorted array. This is the sorted section, and this is the unsorted section, right? So now if we have to complete the sort, we'll have to go one more iteration, right, and put 2 at its place, that is here, right? So finally sorted array, right, and after this the array is sorted, right? But we just, in this question, we just have to report the status of the array after third iteration, right? So what is the status after third iteration? That is 13, 17, 25, 31 and 2, right? So this should be the correct answer for this problem, right? So what will be the order of elements after third iteration? So this will be the order of elements. Now let us take another problem, right? Let's have an array with these numbers 5, 15, 5, 4, 18, 12, 19, 14, 10, 8, 20, right? So again, order after 3 iterations. Okay, so we have to report what will be the order of the elements in this array A after 3 iterations, right? So let us write what will happen after the first iteration. So the 5, since 15, we assume that the first element is the sorted array, because a single element by itself is, by definition, is sorted, right? So we take 5 and we put it at its place. So after first iteration it becomes 5, 15, 4, where this is the sorted now, 18, 12, 19, 14, 10, 8, 20, right? And this is the unsorted. We perform the second one. So we take 4, we put it at its place, right? So it will become 4, 5, 15, 18, 12, 19, 14, 10, 8, 20, right? So this is the sorted, this is the unsorted section. In the third iteration, we take the element 18 and we put it in its position, so that will be after 15. 4, 5, 15, 18, 12, 19, 14, 10, 8, 20. This is the unsorted section. So right, so after 3 iterations, what is the status of the array? What is the order of element? It is 4, 5, 15, 18, 12, 19, 14, 10, 8, 20, right? So again, this is what we are looking for, not the complete sorted array, but only the order of elements after third iteration or fourth iteration or fifth. Like if we had to go for a fourth iteration here, right, what would have happened? We would have took 12, and then where does it go? After 5, before 15, right? So after fourth iteration, it will look something like this: the sorted section and the unsorted section, 10, 8, 20, yeah, and so on. Like we just need to take the value at the first value in the unsorted section, and put it at its place in the sorted array, because it's just like we just need to search which one is the next largest value in the sorted array and then put it just before the next largest value, or if the value itself is the largest, as in this case, we put it at the end of the sorted array, right? So 19 will come here. So this is basically about the workings of the insertion sort. Now let us take another problem, right? Let's say we have the equation representing the number of steps taken for by any algorithm for n elements, right? If it is like this, okay, so if let's say f of n is half n squared minus 3n, then what is the theta f of n, right? So again, whenever we want to talk about computational complexity, right, so it is basically in, right, complexity when n goes to infinity, right, for very large values of n. And if we look at this function, right, so 1 by 2 n squared minus 3n, right, so as n grows, or like theoretically goes to infinity, n square becomes really large than n, right? So it means that n squared minus 3n, right, this value will be dominated by this term, right? So this linear term will be negligible for very large values of n as compared to this quadratic term, right? So if we, okay, so right, so this implies 1 by 2 n squared is much larger than 3n, right? So basically we can say that we ignore this term, right, because it is very small compared to this. So as n approaches infinity, f of n is approximately 1 over n squared, right? And now we can see, since the order of n is 2, so the time complexity of f of n is O of n squared, right, theta of n squared. Now again you can see that this f of n and this n of squared, only n of squared, their time complexities are the same, but the functions themselves are very different, right? So that is also one example for this problem that we took in the first place, that even if the time complexities of two functions are same, that does not mean that the functions themselves need to be the same, right? They can be, but that is a special case, right? In general they are not the same. So let us take the next problem. If the time complexity of f is, or let's say if f and h both are O of n, then we need to comment on first, or we can just create options, right? So is this option true or false, right? H of n or O of n, B f of n plus and h of n. So right, so first option is f of n plus minus h of n. So if we add the two functions or we subtract the two functions, right, the time complexity still remains of the resulting function O of m, right? If we add, then it is O of n, but the subtraction is not O of n, or conversely f of n minus h of n is O of n, but f of n plus h of n is not O of n. Or basically we can say that we have incomplete information, right? So which one of these is true? Can we conclude about the time complexity of the resulting function if we add, subtract, or whatever we do with the two functions, if we have the individual complexities of the functions, right? So let's look at it like this. Let us assume that f of n is n plus 2, right? Just assumption, right? And h of n is, let's say, 3n plus 4, right? So, or let's take it like this, right? 3n plus 2 and n plus 4. So let's add them, right? So this becomes 3n plus 2 plus n plus 4. So this is 4n plus 6, right? And if we subtract them, right, then it is 2n minus 2, right? Now what is the time complexity of 4n plus 6, right? So it is basically the same as the time complexity of n, right? Because it's linear, the order is like it's linear in n. And what about 2n minus 2, right? Again, for very large values of n, this is also O of n, right? So by an example we saw that irrespective of whatever the form these two functions take, if their individual time complexity is linear, then their subtraction and addition both will be linear, right? So it's not just for this particular example, it is true if we take any general case, right? If we, let's say, because this is the general form for any function that has a time complexity of, that has a linear time complexity, is c3n plus c4, right? So f of n plus h of n is c1 plus c3 n plus c2 plus c4, and f of n minus h of n is c1 minus c3 n plus c2 minus c4. So of course, this is O of n given that c1 and c3 are positive, right? Let's say if all of them are positive, right, then this is O of n, no doubts. But here we just have to, for c1 greater than c3 and c1 minus c3, and for n greater than 1 and C1 minus C3, like of course greater than C2 minus C4, right? These are just constants that should come this way if this is the valid runtime complexity calculation, right? So this is also O of n, right? So if you add or subtract two algorithms with linear time complexity, you end up with an algorithm of linear time complexity. It does not change, it does not increase or decrease. Now this is not the case if we multiply the two functions, right? Because if you multiply two linear functions, then the resulting one, the resulting algorithm can be like squared time complexity, right? But we are not discussing that here, right? So given linear time complexity, both of them are O of n, right? The addition and subtraction, both of them are linear. So the first option is correct, right? And we do not have incomplete information because that this is all the information we need that to comment on the runtime complexity or asymptotic complexity of the addition and subtraction, right? So we do have complete information, and with that we concluded that the addition and subtraction both will be linear, will both have linear complexity. Right, so let us take the next problem. So, well, what strategy or approach does merge sort use? Right, so which strategy does merge sort use? Right, so we know that in merge sort, if we have an array, right, so we partition this array, right, and then we keep partitioning the array recursively, and then we merge, right, those two partitions when they're sorted, right? So basically we reduce it till we hit the definition of being sorted, right, where we have just two elements, right, and then we merge them in such a way that they become sorted, that we end up with a sorted list, right? Same for the other two leaves, right? And then since both of these are sorted, we merge them again to make a sorted array again, right? And this keeps happening for all the different partitions of the array, right? So basically we are dividing this array until we hit the definition of sorting, right? Until we hit the single elements, and then we sort them, right? So of course it's not greedy, right? It's not a heuristic based approach because again we are not taking any heuristic about how we divide or how we sort these array. All of these are like well defined, right? And essentially what we do in merge sort is we divide and conquer, right? Basically we divide each array and then we sort after dividing, right? And since it is recursive, so by definition whenever we start sorting any two arrays, they will between themselves be sorted, So let's take another problem. If all elements in an input array are equal, right? Let's say for example is this, right? So in that case, what is the running time or the complexity of insertion sorts, right? So the worst case complexity is n squared, that we have already seen, right? Because we have to traverse the entire array at least once for each element of the array, right? So it is basically n times n elements, so right? So it's basically n squared operations at least, like in the worst case, right? But what is the runtime of insertion sort when the array is already sorted, right? So basically an array with all entries equal is sorted, right? So how do we start the insertion sort? We basically check if the array is sorted, right? If the array is sorted, we basically stop there, right? So the runtime complexity of insertion sort when all elements are equal is equal to the runtime complexity of checking if the array is sorted, right? And what is the runtime complexity of checking the array sorted? We just have to traverse the array once, and traversing the array linearly is O of n, right? So the runtime complexity of insertion sort for the types of array when all the values are equal is linear, right? It's not the worst case complexity, it's just the complexity for this particular case, right? Let's take one more problem. Right, so let's consider two arguments. We have the theta n log n, right? It grows more slowly theta n squared, and second, the worst case time complexity for merge sort is O of log n. So basically we have to select the correct option, right? So first is that both are true. Second is only second is true. It means that the worst case time complexity of merge sort is indeed O of log n, right? Worst case. Or only one is true, right? So n log n grows more slowly than n squared, right? Or d is both are false, right? So let's take the statements one at a time, right? So, well, you see, theta of n log n so how does log n grow, right? And we can say that the first one is n times log of n, and the second function is n times n, right? So since if we are talking about monotonicity of functions, monotonicity of the composition of two functions, then, or in one way multiplication, then if one function is the same, right, and is monotonic, then the monotonicity of the second function determines how will the resulting function behave, right? So log n from n equal to 1 grows like this, right? And n from n equal to 1, right, grows linearly, right? So now of course if we multiply n to both of them, right, like it will just change the shapes of the function, but the relation or their respective positions will not change. For example, this n log n will become a bit linear asymptotically, right, and this n squared will grow quadratic. So again we can see that the growth rate of this function is less than the growth rate of this function, right? Of course, for very large values of n as n tends to infinity, right? Because growth rates at the start, right, of course these functions are not exact, but the growth rate at the start or for smaller values of n will be comparable, or it can even be lower for n squared, like let's say for n equal to 1 or n equal to 2. But for worst case, right, this will always be slower than this, so the first argument is correct, right? And then we need to comment on the worst case time complexity of merge sort. So just a second. Yeah, so we have to comment if the worst case time complexity of merge sort is whether it's of log n, right? If it's like binary search type of efficient, right? But we know that, like in the lecture notes you have seen that the worst case time complexity of merge sort is n log n, right? And it's not log n. So the second argument is false, right? So basically first is true and second is false, right? So it means only one is true. So option C is correct. So I think we can try to go over the problems again. I will just quickly go over them. So the first problem, in this we understood that if the time complexities or the complexities of asymptotic values of two functions are equal, that does not mean that the functions themselves are equal, right? And we proved it with an example. Then again we just uh, confirmed, or we just selected what is the operation that insertion sort uses. Basically the operation we had to comment on, right? How to move the numbers from the unsorted section to sorted section. So we know that we basically do swapping of the first element of the unsorted list with in the sorted list, right? And then we had to show the states of the array or the order of the number after certain number of passes of insertion sort, right? Even if the array was not completely sorted. And we did two examples of that, right? So again, in insertion sort, we take the unsorted section, right? And then we take the first value, we put it at its place in the sorted section, right? And then we grow the sorted section, we reduce the unsorted section. And then say again we take new, like the new first value of the unsorted section, we put it at its place, right? We find its place, we traverse the sorted array, and then we put it at whatever place it should be in the sorted array. So yeah, and then we how we actually calculate the time complexity for any given runtime function, right? And then we just saw some basic properties about time complexities, right? And if we add or subtract them, they basically how they behave. And then we just briefly commented on the strategy that merge sort uses. So yeah, I think these should be enough for week 1 assignments. And again, if we just look at it from the sorting perspective also, right? So we just sort, or not sorting, the swapping perspective, we take the first element and then we swap it with the next largest element, or not the next largest, just the element that is larger than this in the sorted array, right? So we just swap 5 and 15, right? So we swap 5 and 15, and then we start again with this array, right? And then we take 4. Yeah, I mean, it's pretty much clear. So I think I'll stop the recording here, and I will take a similar session next week. So see you guys.